Okay, for today we are going to do chapter 12.2. This is chords and arcs. So there's a lot of theorems in this with their converses, so I'm going to skip a couple of examples. I'm going to try and go through pretty thoroughly these theorems and their converses and make sure you really understand what the theorems are saying. So first of all, we got to talk about what a chord is. And a chord is simply any line segment in a circle where both endpoints are on the circle. So that could be a diameter, okay, but it doesn't have to be, right? So if you had any circle, and this is the center, a diameter could be a chord, but then so could this, just some line where both endpoints are on the circle. Excuse the terrible drawing, but I think you get the idea, okay? So your first theorem, like I said, the theorem, and then it also has its converse. So the first theorem says, within a circle or congruent circles, congruent central angles have congruent arcs. And we've kind of already talked about this, okay? Because remember, think back to chapter, actually it was 10.6. If I told you that this angle here was 60 degrees, you knew that the arc measurement was the same thing. Okay, but if this angle is 60 degrees and this angle is 60 degrees, then that arc measurement is also 60 degrees. So it's always saying that if you know that the central angles are congruent, then their arcs are congruent. And then, of course, the converse is going to say if the arcs are congruent, then the central angles are congruent. So if I know that this arc measurement is 50, that arc measurement is 50, then these two angles must also be 50 degrees as well. Okay? Next theorem, within a circle or in congruent circles, congruent central angles have congruent chords. So if you were to kind of take the theorem we just discussed, the one right above, let's stick with this being 50 degrees. If these two angles are both 50 degrees, well, if I were to draw a line from kind of closing in these angles, then these these lengths rather, have to be the exact same thing, okay? And then the converse of that is true. If we have congruent chords, then we have congruent central angles, okay? Third one, within a circle or in congruent circles, congruent chords have congruent arcs. Well, if this chord and this chord are congruent, then this arc and this arc must be congruent. And of course the converse is then also true. If I know that this arc and this arc are the exact same thing, then I can also conclude that these chords must be the exact same thing as well. Okay, so all of these things are true, and of course the beauty of this being a video is you can go back and reread these or listen to me read them or whatever it is that you need. Alright, so a couple of examples. I'm going to skip one of them. I'm going to skip this example here, and I'm going to do this one. Very straightforward. In the diagram, circle O and circle P. I'm sorry, circle O is congruent to circle P. Given that BC is congruent to DF, I apologize if you hear my daughter in the background. What can you conclude? Well, we can conclude several things. Okay, one of the things we can conclude is that angle BOC and DPF are congruent. Okay, and we could also conclude that arc BC and arc DF would be congruent. Okay, so those are just a little bit of brushing up on all three of those theorems we just discussed. Like I said, we're going to skip this example. We're going to jump down to, of course, more theorems. This one says, within a circle or in congruent circles, chords that are equidistant from the center are congruent. Okay, so let's back up here a minute. Equidistant means it's the same distance. So in this picture, if I know that chord AB or BA, and I know that chord CD if I know they are both 3 units away from the center. So that's what this is showing here. It's showing you that this piece and this piece are congruent. I just made up the number 3, just to, whatever. But if I know that AB and CD are both 3 units away from the center, then I know that these chords have to be congruent. Okay? And then the converse of that is also true. So within a circle or congruent circles, congruent chords are equidistant from the center. So if I knew or told you that in this picture, chord AB was 7 units long and chord CD was 7 units long, then you could conclude that they are both chords are the same distance away from the center. Okay, because the chord lengths are the same. So let's go through this one more time. If I tell you that chord AB and CD are both the same distance away from the center, then you can tell me that the chord lengths have to be the same. And then on the converse of that, if I tell you that this chord length and this chord length are the exact same value, then you can conclude that they are the same distance away from the center. Okay, and remember, just a side note here, when you measure distance, okay, that does make a right angle. So when you measure something like how far away two things are, you always want to hit at a right angle. That's going to come up into play here in a little bit. Okay, so your first example, Okay, our first example is asking you for the length of RS. So how long is RS? Okay, well, in this picture, I have another chord drawn down here, PR. Okay, and PR's total length is not given to us, but we can find it. So in this picture, it is given that PQ is 12.5, and PQ is congruent to RQ, so this is also 12.5. So the length of PR is 12.5 plus 12.5, which is 25. Okay, so that's not anything we learned. That's just segment addition postulate from chapter 1. Okay, they told me that from here to here is 12.5. This length is the exact same length as this length. So take 12.5 and add it to 12.5, and I get the whole thing to be 25. Now, OQ and this distance, these two chords are both 9 units away from the center. So now the theorem that we just talked about does come into play. If you have two chords that are equidistant from the center of a circle, then those chord lengths are congruent. Therefore, the length of SR is equal to 25. Because SR and PR are both 9 units away from the center, and if PR is 25, then SR is also 25. Now you should take a minute, try the next one on your own. You should pause it, and then we'll go over it. So here we go. For this one, they're looking for the value of for X. Justify your answer. Well, in this case, this chord. Its total length is not given to me. This chord's total length is given to me as 36. The total length of this chord is this part plus this part, which 18 plus 18 is 36. So now I have two chords that have the same length. They're both 36 units. That tells me then the distance that they are away from the center must be the same. So if this chord is 16 units away from center, then that means that this is also 16 units away from the center. Therefore, X is 16. Okay? And then justify your answer. You could say, if you want to quote the exact name of the theorem, I already don't know what it is. It's theorem 12, whatever. But I would just say your justification is you have two chords that are congruent are equidistant from the center. Okay? Alright, last round of theorems and then 2 examples, and then we are done for the day. Alright, so again, these are 3 theorems. There's no converses here, so let's make sure we get these down. So in a circle, if a diameter is perpendicular to a chord, then it bisects the chord and its arc. Okay, so here we go. Here's your diameter, AB, and I know it because it passes through the center. Okay, this says if this diameter is perpendicular to this chord, then it's going to bisect both the chord and the arc, as shown here. Okay, so if I tell you the diameter is perpendicular to any chord, it's going to bisect the chord and the arcs. Okay? Now, in a circle, if a diameter bisects a chord, that is not the diameter, then it is perpendicular. So, this is kind of the converse of what we just said. Here's your diameter, and it bisects this chord. Well, then the conclusion is you get a right angle as shown here. Okay? Lastly, in a circle, the perpendicular bisector of a chord contains the center of the circle. So you have, in this picture, you have two chords, right? Right now, this is a chord, and this is a chord. Well, if AB is the perpendicular bisector, then AB must contain the center of the circle. So this is kind of tying in the first two theorems all together. Okay? All right. Two examples, and then we're done. So for the first, for both of them, I think they want you to find the value of x, or the variable rather. So let's take a look at example A, and it's telling us that this length is 14. They're asking for this length right here, which is the radius of the circle, and we know that this little piece is 3. Now, the theorems all talked about the diameter, and in this picture there is no diameter drawn. However, if I were to take the dotted line that's in red and I were to continue the dotted line, that is the diameter. Okay, Kn is a piece of it. They just didn't draw the whole thing. They cut it off. Okay, they just drew this much of it. But it is the diameter because it goes from the center and it comes all the way up. Okay, they just didn't draw the whole thing. Well, my rules tell me if the diameter is perpendicular to a chord, which it is in this case, then it bisects the chord. Well, if the whole thing's 14, half of 14 is 7 and 7. Okay, so I really just need to pay attention to this triangle. Okay, and then I can solve for r. Alright, so I had to use the theorem that tells me that if the diameter is perpendicular to a chord, then it bisects it. So now, all I have to do is solve this triangle here for r. And it says I can round to the nearest tenth. So 3 squared plus 7 squared is equal to r squared. Alright, that gives me 9 plus 49 is equal to r squared. And 9 plus 49 is 58. And then square root both sides. And let's see here. That gives you 7.6. Okay? So your answer for R is 7.6, and that's even after you round your answer. Okay? Moving on here to number, or letter B, I would personally Actually, in class, if this were in class, I don't think I would let you do this on your own, because this one is tricky for one small detail. But once you see it, it's not that bad. But if you want to try it on your own, by all means, pause it and then check it. But usually when kids look at this, they panic. Okay, they look at this and they're like, all right. They understand the process. Like, I kind of create a triangle, and they're looking here and they're like, okay. So I go to make my triangle. Then I've got my 11 here, I've got my y, and they didn't put a value there. So now you're like, all right, I got two unknowns, I don't know how to solve it. Well, a couple things are going on here. First of all, let's understand the fact that much like the problem before, they didn't draw the full diameter, right? CB is part of the diameter. If I were to keep drawing it, right, I know it's not a straight line, but okay, and it bisects this chord. So I think the middle theorem of those the last three that we talked about says, if a diameter is a bisector to a chord, then it makes a right angle. So, no, the right angle doesn't tell me that length, but it does tell me that is a right triangle, so I am able to use the Pythagorean theorem here, which is a good thing. Now, the issue here is you still don't know that length, but you actually do. Right, BE and AB are both radii of the same circle. Okay, so if BE is 15, AB is also 15. Okay, so now you have your triangle. 15, y, 11. So when you go to set this up, 11 squared plus y squared is equal to 15 squared. Okay? When you square 11, you get 121. And y squared is y squared, and 15 squared is 225. Minus your 121 from both sides, and I think you get 104. Okay, and then we got a square root both sides, and y comes out to be, I believe, 10.2 after you round. Okay, so those are your two examples here. So keep in mind on your homework that when you get a problem like this, and there's going to be times in your homework where they're not even going to have this dotted line drawn, right? You can redraw the radius of a circle wherever you need to create your right triangle. Okay, so they might give you a picture, that looks something like this. And then we'll do that. We'll do this, and they'll draw the radius over here. And this is both, 7 and 7, that's 2, and you're looking for that value. You can redraw the radius wherever you need to create your right triangle. Okay, so if you get your homework and you don't have a triangle in the circle, you don't panic, you can make it. Just redraw your radius wherever you need to. Alright, hopefully this was helpful. If you need any help with your homework, please shoot me an email and I'll post a video as soon as I can. Take care.